My name is Conny. I work at MAX4 as a beamline scientist and lead for the RIXS team. I come originally from Uppsala, so part of the RIXS group in Uppsala. That's why you see some mentions of Uppsala in this talk. Should I close the door? I will give an introduction to RIXS and especially to RIXS at MAX4 and what we can do in terms of soft X-ray RIXS. Is what we'll be talking about. Part of my team is here, so I can't unfortunately lie to you, stick to the truth. But yeah. So resonant inelastic X-ray scattering RIXS. First of all, why spectroscopy? If I understand correctly, not all of you have backgrounds in spectroscopy, but you've been listening to spectroscopy talks now for 2 days. But just to make the argument, you have a few ways of using X-rays looking at matter, which is what we do at MAX4. Imaging techniques like microscopy is one important part. You have indirect imaging, diffraction. That's about the geometrical structure of materials. And then we have all the spectroscopic techniques, which actually is a huge part of what we do at MAX4. We learn about the electronic structure of the materials. And then, of course, we have combinations of the three, so to say. And spectroscopic techniques are very useful to understand materials because the electronic structure gives rise to a lot of the microscopic properties of materials like magnetism, optical qualities, and all of those things, which I'm sure that you are aware of. But I still just want to mention it in the beginning that what we'll be talking about is essentially spectroscopy, even though it says scattering in the title. So, but RIXS is, to all purposes, a spectroscopic technique. So, a small history lesson. So after the discovery of X-rays, of course, they tried to use it in all kinds of ways. One of which was that you discovered the characteristic radiation of different materials as a way of finding different materials, identifying them, and so on. And you had very early law that you had set proportional to the square of the energy of the X-rays. So this is already in the early 1900s, where this was quite advanced. You continued, and you also found more uncharacteristic or valence-like X-rays. So this is the early days of X-ray emission, where you found that you can actually learn information about also the valence state by creating core holes. So an example here is from 1935. And then, of course, electron spectroscopy that sort of took over the business once discovered and once really developed. And the highlight, of course, is the Nobel Prize to Kai Sigman in 1981. I mentioned I was from Uppsala, so I have to mention Kai, otherwise I get my Uppsala license revoked. So this is of course a very, very important part of especially surface science, which is a big part of material science and understanding things like catalysis and chemistry and so on. So this did take over, but so many people maybe forgot about his father, which was Manne Sigman, who actually started out in Lund, but then moved to Uppsala. And he had his Nobel Prize already in 1924 for the manufacturing of high quality gratings for the use in X-ray emission spectroscopy. So this is maybe, I mean, for this talk, this is the more important Nobel Prize in many ways. And they were used in soft X-ray region. They used E-beam excitations because they didn't have X-rays. X-ray tubes is a bit too weak to do these studies, but a lot of E-beam excitations, just creating core holes like crazy and then measuring what you could see. And then they really pushed the resolution of the instrumentation by the quality of the gratings they could use, and more refined the way how to mount the gratings and the detectors, which at that time was photoplates. So very high resolution, but quite time consuming. But again, with the advent of tunable X-rays, you can do a lot more with X-rays, and that's what I'm trying to talk a little bit about. What you can do, and this is where X-ray emission transforms into resonant inelastic X-ray scattering RIXS. Please stop me for questions, but I understand Alexander correctly. You typically do questions at the end, but stopping me is absolutely fine. So here is a picture of a very early X-ray spectrometer. This is you had physically the focal condition made in metal, and then you just put your grating, your electron beam source, and then your photoplate along this curved surface. You pump down, and then you started the E-beam, and you went away for a while, and you came back. You developed the photoplate, and you found you're slightly out of focus, and then you move the photoplate. So a typical acquisition time for a spectrum then was around 3 months, if I understand correctly. So it took quite some time. So, but it worked very well. Actually, we're still struggling to reach the resolutions that they were able to achieve. Down here is a development for that. That was the first commercial X-ray emission spectrometer developed by Såthe together with the group in Uppsala, so you can actually buy them commercially. It's so X-ray RIXS starts with absorption, and I think you had a probably extensive talk by Konstantin the other day about X-ray absorption. So absorption is basically you create core hole by absorbing a photon. You can either do it just shoot with high energy, and then you just kick the electron out to continue. This is then non-resonant, that's what we call it. Or you can fine-tune the incoming photon with a synchrotron, and you can really put it into one of the empty states. This then creates the resonant part of the RIXS. And this is, of course, a very powerful technique in itself, and it's of great use to understand things. So you can measure it in many different ways. Just drain current. You can do it by MCP plates. Put different meshes in front of it. Create partial electron yield measurements. You can do it in the fluorescence channel by an MCP plate, or even use a spectrometer to get a partial fluorescence yield. So there are many degrees of refinement here that you can do, and we do that. X-ray emission then is the second part of this process. So you created your core hole, and if you did it non-resonantly, one of the valence electrons will fall down and fill that hole and emit a photon in the X-ray region. And that the energy of that X-ray will then give you information about the valence state that you have. You can do it resonantly, and then you have two options. Either one of the electrons from the valence falls down and fills this state, and leaves you in a valence excited state because you still have the other electron there, or the electron that went up could just fall down and fill the hole. That's sort of an elastic scattering, but things can happen in between, and they do. So which means that you will have small energy losses, and with the modern spectrometers, we can actually detect that energy loss. And this is really where this is the proper RIXS that we're talking about, when it's resonant and it's inelastic, and you just have small energy losses. And this is all that we'll talk about mostly. But there's also a lot of information to find in the valence transitions that we have. I just added the equation for the whole thing up there for you to have. I won't go into any mathematics or anything. So, furthermore, these core levels that were exciting, they are quite atomic-like. They're very localized on the atom where you do it. This means that X-ray emission, or RIXS, is a very local probe. It gives you information about the partial density of the state from that atom. So it is a very useful technique, and this means that you can use this to detangle. If you have several different atomic species in a material, you can look at one or the other edge, and you will get sort of parts of it. It's fairly complicated. I should warn you, you need a theoretical partner to fully understand this, because you will need to do, those calculations to understand this. And remember, absorption probes the empty states. this is the first step. But then, of course, we do get information about the partial density of states, the filled ones with core hole, but you always need to consider the core hole present. We have furthermore, since we have a photon out, photon in technique, we have things like symmetry selection rules for the lower energies. So that adds more tools for us to manipulate things and understand. I will show you an example where we use this later. So, in short, resonant inelastic X-ray scattering. It is, first of all, a one-step process if you want to treat it mathematically properly. You can easily think about it as a two-step, an absorption followed by an X-ray emission, the way I described it. But in the end, when you do the final analysis, you need to take into consideration that it is a femtosecond process. And this means that you need to consider both steps at once. And this gives rise to several phenomena that you wouldn't be able to explain otherwise. It's element and orbital specific. It has a very high chemical sensitivity. Actually, it cannot only discern different atomic species, but it can discern easily different atomic species in different chemical environments. So this gives us a very powerful tool that we can do a lot of things with. It's a local probe because of the core hole involvement. So, and it gives information about the local electronic structure and dynamics. It's bulk sensitive. Again, it's a photon in, photon out technique. So this means that you can penetrate quite a bit down. How far depends on the energy. Low energies, low penetration depth, almost surface-like. But for things like oxygen, copper, and those edges, you will go down a few thousand atomic layers at least. You can get information. And of course, manipulating the geometry of your sample will help you determine which depth probe you have. We can monitor both the energy loss, but also the momentum change in the scattered photon. This means that we can look at things like band structure, which we'll hear much more about tomorrow from my colleague Aniroda, who will give you a talk about quantum materials, where this is very much of interest. So dilute samples, because of this high sensitivity that we can tune to a specific atom in a specific chemical environment, this gives us the possibilities to look at really dilute samples and small sample volumes, limited by the size of our X-ray beam, essentially. We can even look at buried layers. I have looked at buried monolayers under a few hundred atomic layers of another species. It's clearly quite possible. You do have a polarization dependence. So clearly being able to measure and control the polarization of the X-rays is also an important factor when you set up your RIXS beamline. And we have no charging problems. So semiconductors is not a problem to study with. So that's sort of the short of it. Let's see. One thing to remember, though, that there is a big drawback, especially soft X-rays in the soft X region. And this is, there are two ways for this core excited state to relax. One way is the one we want on the right, the radiative one, where we send out an X-ray, and those are the photons that we want to measure. However, the electrons can directly interact with each other and decay through an Auger decay. And at these low energies, the overlap between the electrons are typically quite large. So if you look at the right-hand side, you see the fluorescence yield as a function of atomic number, K shell first, L shell later. And as you see at these lighter elements where we are looking, it tends to be very, very small. In fact, it's notoriously low count rates. So it's 0.1% or less of all the events that you'll be able to do. And this is probably one of the main reasons why RIXS hasn't taken off until you now have these super bright fourth generation sources. Measuring a RIXS spectra is typically on the order of hours rather than minutes with high resolution instruments. So it's quite time consuming, but the amount of information you can extract is very, very big. I like to put this in front because it's important to remember when you go to your first RIXS beam type. Be relaxed. and the quality of data is quite important. Now, a note of choices on how to design your instrumentation is this is a very famous picture from Ahmet and et al. A RIXS overview paper, and it was found that these energy losses on the elastically scattered photon is you have all these phonons and magnons, which are very important and interesting things if you look at quantum materials. This means that the area of quantum materials has come to dominate the RIXS field in the last few years, especially, and been a very much a driving force behind building all these high resolution RIXS beamlines. And this is visible in the way they are built and designed. It is a very important field. It's something that we definitely want to do. I would say that about 60–70% of our science at the moment is solids in one way or other. But this has led to most RIXS beamlines being built with in-vacuum goniometers because of controlling the incidence angle is so important, with large chambers with UHV as a standard for your experimental chambers. Even in many cases with the optics inside the experimental chamber itself. This means that they're fantastic for these materials. But if you want to do something more exotic or more towards chemistry, or even looking at batteries or catalysis or something like that in situ in operandi, which is also something that's of interest, that is something you cannot even attempt to do in these chambers. And this is one of the things that fed into how we designed Veritas, which I will talk quite a bit about. So just to explain to you, this is how a typical RIXS spectrum looked in the early 2000s. So what this is, if I explain what it is, this is nitric oxide on the oxygen edge, exciting on the pi star, the first resonance. What you have here is the elastic peak. You see energy loss. So clearly something's happening with this elastic. And you have then valence excited final states. And if I do this systematically, I will see a lot of variations in these coming. But this is what I see. So I can of course do a lot of calculations. This is of course vibrations. So this is vibrations being set up because of the excitation. I can fit this to my the expected lifetime and so on, and do a lot of things. This was published, so it's the thing to do. But there's clearly more happening here. So if I only had better resolution, I could actually see if this is a python who just devoured an elephant, or if it's just a fat python. Right, so this is an example from the little things. Sometimes we can be clever, but it's still we want to see stuff, right? Exactly what it is. And this is in fact the same spectrum measured 2012 at the high resolution instrument, and clearly you see there's a forest of different vibrational progressions in here that would be very hard to get extracted properly. There's even some dynamics happening there that I don't understand. You see these lines. It's also a lot of vibrations in there that maybe wasn't expected. So clearly it's worth trying to offer high resolution RIXS also to other fields outside of the quantum materials. So that's my job now, to try to convince you. And then Aniruddha will bring you back to the quantum materials tomorrow. So there's a lot of things we can do. So I figured I'll just take one example from the old times. This is the oxygen molecule, O2, inversion symmetric. This means that you have strict selection rules. You will have only gerade, ungerade, gerade transitions to the photon, because you need to change by one. So what we did, we measured a series. So this is then measured on the first. This is this excitation, which it goes up there, and then you have the gerade going down, as expected. You only see a single one. At the top, you see all of them because this is electron excited. You have no selection rules. So there you see all of these different levels represented in your spectrum. So clearly that's this one that we see. If I excite on the next one, that means that I then go with this one all the way up from the gerade to ungerade. I mean, I now separated the core levels, but they're not really separated in real life. Energy-wise, it's hard, but because I have this ungerade and gerade different excitations available to me, I can discern them anyway. So this is what happens there, and then I should see only the ungerade. So if I go to that excitation, I see that the spectrum has changed. We lost this one, and as you see, the elastic peak has moved. Of course, it's not completely pure because you're never completely pure in the energy of this. So that's clear. This holds, and then you can go through the rest and do the same. And of course, you compare it to the electron excited, where you can see all the different states that you have. Then you do the same thing here. What you do then is you don't just, because with the first one, the resolution is only enough to like whack the whole excitation with a hammer, essentially. So it's a very broad excitation. Here we can really narrow the excitation, just excite on different parts of the vibrational, which you also see is present in the absorption. The top one is the absorption. And then we do those excitations over the first one only, and you see that this holds. You get more and more of these excitations. You even see stuff like here. That this dip you see is what is called a quantum beat, because you cannot discern between the two different core sites. You will get a beat like a double slit excitation. Essentially, this is quantum mechanical phenomenon. So clearly, I mean, you get more information, but you also get some of the same, but there's more to see down here as well. So these are the same experiments conducted essentially at two different beamlines. One was the Advanced Light Source, Berkeley, and the other with a very short instrument. This is with a 5-meter instrument from the Swiss Light Source. You can also then start looking at really lifetimes, trying to figure out what's going on with the nuclear dynamics going on. So we can start really measuring the scattering duration time, and then we can figure out the lifetimes of these things. I won't go in. So basically, these are the results for the coronal lifetime. You see, if you detune, you get a shorter coronal lifetime, and as you go up, you allow it to exist longer, and that shows up in then the progression that you have. You can take this one step further and start looking at. So this is again oxygen, all of it. You can look at different compounds. Essentially, if you have an OO bond, it looks in one way. If you have an OC bond, it will have a different vibrational structure. And then you can start comparing them between, even if you don't have access to a purification. So here you compared then pure free oxygen gas, liquid acetone. You make a mixture of acetone and chloroform, where you have a very strong hydrogen bond present. And you can also then compare to liquid water and so on to understand. And what we were able to discern here is actually you get the presence of a hydrogen bond starts bending then your potential surface. So if you put the outer, I mean the higher excitations on this pi star, you start getting distortions because it's no longer like in the O2, it starts bending it. And you can even quantify it to some extent. So down here, you see this very strong bond or effect on the vibrations in the acetone chloroform bond, where you have a very strong presence. So these are things that people are now exploring and trying to figure out. So clearly, there is a use for chemists even, and quite basic atomic and molecular physicists to look at that RIXS data and learn more about things. So I thought I'd just, before returning to the science, I'll talk a little bit about instrument design. So essentially, a RIXS instrument is very easy. You have a source. In the old time, it was a slit. Now it's the spot itself from the synchrotron. You have a grating. You can rule the grating differently, different line densities. You have a detector that detects it or records the image, photo plates, CCD detector, or an MCP detector with a delay line anode or something like that. So this is the basics. Then of course you can have different, line densities, varying line densities, and so on. But basically, this is how you look at the resolution. So it's dependent on the source size. So you need a small source, ideally. Groove spacing, you need high groove spacing, but high groove spacing will cost you intensity. And it doesn't go linearly, it goes far worse than that. You have order of diffraction. So you can always look at first order diffraction, but then of course you have second order, like you can see double rainbow sometimes. That will pull your lines further apart at the cost of intensity, always. And then of course you have the grating radius. The larger the grating radius, the higher resolution you can achieve. And that's the reason why you see these spectrometers becoming long. I think you went and visited Veritas on Monday and saw it. It's a 10-meter instrument. There are also 15-meter instruments in the world. I mean, the further you can pull the light apart, photons travel along a straight line. So the further you can pull them apart, the easier you have to detect it. And to note, this is assuming you have an infinite resolution in your detector, of course, because the detector will start limiting you fairly soon. But these are the parameters that we can play with. And then you can maybe understand why the RIXS instruments are so big. Because the magic button of group spacing turns out to be very, it really kills your performance above 2000 lines per millimeter or so, then it gets a struggle to measure. Source size, that's probably where you can do a bit more. Already there at Veritas, we have a 1 micron source. But that's probably the limit, and then you will run into problems with stability. Order of diffraction, that's something that you can play with, but that means you can't use these very line space gratings and so on. Then you need to start tailoring your design to specific emission lines. You want an instrument that can do many things. This is then the design of the instrument at the address, which was the first high resolution instrument. It's a 5-meter one. So as you see, it's a very simple design. The main problem is you need to keep everything stable and you need to be able to move your detector. So this is the instrument they've been built at the SRF. It's for some 15 meters long, and the highest position for the detector is 4.5 meters above ground. You get a lot of engineering problems here. It works very, very well, beautifully. But it's fairly complicated and time-consuming to optimize it. It's also fairly expensive to make and takes a lot of space. This is the beast they are built at the NSLS-2 synchrotron in Brookhaven, outside of New York. As you see here, they've extended the beamline outside of the building itself and built a separate building to house this big spectrometer. So it's and in general, the longer the beamline, it's the same is true. Then you can lose lower number of lines per millimeter in your grating, and that means much higher throughput. So it's always a match between. You can have 1 million resolving power, but then you have 1 photon in the experiment. And that's not going to help you much. So it's always a trade-off. So Veritas beamline, what we've shown you. It's beamline itself, it's designed for 50,000 resolving power. Unfortunately, we also wanted to go outside of the building, but budget forbade it, so we couldn't do it. So our beamline is about 55 meters long. It's the longest soft X-ray beamline you can find at max 4, but it's the other beamlines are about 90 meters or so. So it's clearly limiting us, which means we have to have high rule densities for these higher resolutions. So this is still limiting us to some extent because it's hard to find the ratings on the quality, but also it puts the demands much higher on everything else, on the stability and everything, because you really can't allow for any vibrations or any heating drifts or anything like that. The range is 250 to 1600 eV. So this means that we want to go from carbon, which is at 280, 278, up to aluminum K. This is a soft cutoff, right? We can always go higher orders and look at higher energies, but you will lose intensity because it's also optimized, the optics, the coating and everything, and the insertion device and so on. What we have on this on the sample is a 1 by 5 micron spot on the sample. This seems true. I think it's even measured the best is 0.8 even. So we have that in the bag. 10 to 12 to 10 to 13 photons per second at the sample of the wavelength you want. That also seems that we have. And we have an elliptically polarizing undulator, which is almost 4 meters long with 48 millimeter period. For those of you who wants to go into spectra and simulate things. That feeds us, which gives us full polarization control from 350 eV and up, which means we can have polarization horizontal, vertical, circular, both ways, and even elliptical, and start playing with things like that. We also have another beamline where we have a RIXS end station that can do RIXS. This is the species beamline, which is the Alexander beamline, where we have a smaller spectrometer. I'll show it to you later. That can do, I mean, fairly simple things in terms of resolution. But we also have this. The good thing here is with this, for RIXS purposes, is it can go to low energies. So if you want to look at other things like sulfur or so, you can find sulfur L, for instance, at species, which can have some uses. The drawback is, of course, you get very surface sensitive. But we have a high resolution, high throughput, low energy instrument in the works there. And also we designed the 2 end stations. So anything we design for Veritas, we can use at species and vice versa. So this means we can do joint developments for sample environments, which we have done quite a bit. So this is, I'll look a little bit on the Veritas spectrometer. It's a collimated roller spectrometer. We did not go for very line spacing grating, because then you need to be able to turn the grating also. That adds another complexity. We decided to put the grating not like this, but like this. So this turns the light down. So you see our detector is not 4.5 meters above the floor. It's rather 0.5 meter above. Works for stability, but of course it limits how we can play with the line spacing. We need to fix inside those constraints, but it makes the mechanical design a bit easier. It has matching energy range of the beamline. It's 10 meters long. That's what we could fit, and that also is enough considering the limitations in the beamline length. The optical scheme is, first we have a roughly 1 meter long collimating mirror, which is a parabola that collects and collimates the light. This is just to increase the efficiency of the light collection, because typically RIXS, you go out in 4 pi, and then if you only collect a very small part, you lose a lot there, and then you lose 99.9% into the Auger decay, and then it's not much left to play with. So really increasing the collection angle a little bit is important. We have 2 different cylindrical gratings that we use to cover the full range, and also gives us access to second order diffraction, so we can choose resolution or efficiency of detection. We have a novel design of the experimental chamber, which is here on the right hand side, which means that we can continually change the scattering angle plus minus 60 towards the perpendicular for all those angular needs that we have. And this is a unique design that I can mention. It's this whole project is a collaboration between Uppsala University and Max 4. And this design was done in Uppsala they have the most advanced mechanical workshop in Sweden, I would say. So it's this complicated chamber is made out of a single piece of steel. It took about 3 months to machine, but it can hold then 10 to minus 10 inside while still changing the angle in this way. So this means that we can do continuous Q-to-Q measurements if we want to. And we have prepared, if you look at the blue design on the right hand side, that's a polarimeter design where we have 2 detectors and the possibility to put in some multi-layers to be able to measure the polarization of the scattered. This is still in development. but we have all the mechanical pieces we need. We have 2 detectors. So this is a future development. Once we have a science case showing up, then we really want to pursue. So that's something to remember. This is the way it looks in reality. And here you can see it's just along a few different scattering angles. Of course, if you have a one micron spot, you want to be able to take advantage of that. So you want a very stable manipulator to control your sample. And when we looked on the market, there was nothing available that would fit us. Nothing was stable enough, or it needed a huge vacuum chamber. So we decided to design one ourselves. So this is what came out. It has 12.5 millimeters horizontal stroke. It has a 400 millimeter vertical stroke, so easy to. But the main important thing is it has about 5 to 10 nanometers RMS at sample when measured with vibrometer. So it's extremely stable while measuring. We have since measured it, the accuracy, and it has something like between 100 and 200 nanometers accuracy in positioning in sample. So we can easily use it to image samples, and we can take advantage of the fact that we have a 1 micron source, especially for common materials. This is important. So I think we've been down to samples the size of 100 nanometers or 100 microns or so that we can actually look at. So we think this will be important for the future. And looking at, for instance, gas phase RIXS, it's important because then you can use small pinholes as sources. You just have a gas plume out and you can easily find it. So this has proven to be a very useful thing. Both of these developments, by the way, have been not commercialized, but they're available through collaborations. And they are currently being used at the Sirius RIXS end station in Brazil. There's also one manipulator at the European XFEL, and there's interest from a few other places to have it also. So we have published papers on both, so that we want to keep it open to academic collaborators, of course. So performance then, what we have. So we did press pellets of a material that when you put light on it, it produces both nitrogen and oxygen gas. So that's a first easy way of measuring just the O2. And this is then the first measurements of nitrogen. You can see the red one is best previously published, and the black one is the one that we measured during commissioning at Veritas. So clearly, resolution is good. It's nowhere near good enough that we're happy, but it's good enough definitely to do good science with. And below you see the same spectrum I showed you before, on the O2 with the vibrations excited on top of this pi star in the middle. So you have lots of vibrations there. Just to note something that you can see here. Here you have something that's dipole forbidden. That I mentioned some of them are, but they still show up a little bit. And this is something that we took advantage of later. So actually the first Science Advances paper coming out was focused on that guy. I'll show you a little bit of it later. This is just to try to do what we call RIXS map, which is essentially an absorption, where you measure, you change the energy and then you measure for 10 seconds. And then you measure the RIXS spectrum, and here you see that it's enough to get. I mean, these spectra wouldn't look nice if you looked at them one by one. But when you treat the data like this, you can make a nice RIXS map and see all the vibrations developing as you increase the excitation energy. And this is then the emission energy. So this is another tool, and this is where I mean that you could potentially also use it as measuring X-ray absorption, because you can then pick and choose either you follow like a fixed emission line, or you can follow one of the vibrations to see how that develops, and you can produce absorption for all of these exotic features if you want to. So you can cut and slice your data any way you want. So it's important to be able to produce these data and be able to analyze them backwards. And I think Anirudh, again, he also has a separate section on data analysis, and you're going to do a practical at Veritas. So essentially what we do, because everything so time consuming, we record the spectra and then you can sort of replay them in software afterwards and play around with the data that you got. And this means you can also go in and see if things went wrong. If you see something, this is completely unexpected, you can double check your excitation energy if something happened in the synchrotron at the same time and so on. All of these are important because this is just minutes, but expect your experiments to take at least 20 minutes or hours, depending on your sample. And of course, automation is very important. So we want something that's stable, so you can start your pre-program, your experiment, and you can go home and sleep, and then you come back once it's done. And you should be able to trust it. That's also been a lot of focus for us to be able to do things like that, because for RIXS, that is an important thing. This is the second RIXS instrument that we have, and this is one of the commercial ones I told you about. It's a bit refined. We've taken away the slit and made it so it can run slitless. At species, the spot size is 5 microns, not 1 micron, but still, it's very good. It's good enough. You can get rid of the slit. And this is currently in operations, or right now the detector is broken, but we have uses on it. The second instrument there is this low energy that it has worked. So we had beam times on it at BESI previously, but we did a rebuild of it, a redesign of it, and it's now waiting final commissioning at that species. This will give you these high resolutions at the low energies, like 10 millieV. Because the excitation energy is only 100, that's quite easy to attain at these low energies. A drawback again is it's quite surface sensitive and so on. But then we have an instrument that has a huge collection angle. It has a parabola close that collects the light, which means it has some 5,000 nanoradian square or radian square. So it has a potential, but doing RIXS at low energies is tricky. So we need academic partners to try to develop that with good science cases. Again, the experimental station there is built so it can house both those spectrometers, and it's versatile, so we can do liquid jets and things like that there as well. That we do at Veritas. Anything we do at Veritas, we should be able to do here. One thing, because of these long measurements and the high flux you need to be able to produce this, because of the low fluorescence yield, radiation damage is a huge issue for us. So we need ways of dealing with this. Stable manipulator, that helps a lot, because then we can control the scanning. We can set up raster scanning of our sample and always only be on the sample one spot at a time. It's only 1 micron, right? So we can easily use, if you have a fair size sample, it's enough for a week of measurements with a slow scan speed and full control. We have that. And then we want to be able to identify sample damage. So we need some kind of time resolution in our data. With the CCD, that's hard to do, because they collect an image over minutes or 5 minutes. Then you read it out and you get all of it. So you can't discern the beginning from the end. So we use a delay line detector instead, which has somewhere 65 was stated by the manufacturer. I think it's more like 100 picoseconds, which is quite high resolution. That part we use mostly for just signal to noise help. I'll show you how. And then we also added another timestamp that gives us more microseconds and onwards. So this means that because we recorded the measurement, we record every spectra when it arrived, every photon when it arrived. We can always go back and look at changes, which changes in the spectrum, cut different slices of the measurement and look at them individually, compare the beginning to the end, and all of these things that I'm sure you'll see in the practical. To figure out if we have sample damage ongoing, or do we have drifts of the energy and all of these things. It's important. This is how it manifests in the software. So as you know, a synchrotron is a pulsed source, which means that we essentially have X-rays passing by every 10 nanoseconds. We have 100 picoseconds time resolution, so this is something we can easily pick up. So we just look at where the X-rays come, and we see only events coming at these times. This means all of this is background. So this means we can then fold this and only allow spectra within this time region. All the rest we can get rid of. So this means, I mean, the problem between MCP, delay line detectors, and CCDs is that CCDs is very noise free, except for cosmic radiation, which are easily deleted. But this in some way fights that and still gives us this time resolution. And we would not, with the optical design we would not be able to use a CCD because it's grazing incidence. So, and at grazing incidence, the CCDs are not really working so well. for various reasons. This also, of course, sets up different possibilities that we can start looking at. Experiment pulse sources, droplets. We can start looking at supercooled droplets. We can start doing pump probe if we find so. I mean, we can't do it on the FEL scale, like attosecond spectroscopy, but we can do something. If you have chemistry happening at the microsecond level, then we can start working with that with this setup. So this is again something we want to develop further. One of the directions we want to bring into beamline for the future. So, and this, just to come back to this dipole forbidden thing. So one of the first things we did, I mean, of course, we built this mostly for the solid state community, for the materials to look at. I mean, progressions of magnons and so on. You figure that it's useless for a randomly oriented sample. They wouldn't give anything. You wouldn't get a benefit from a gas sample, but of course, the first thing our users wanted to do was to look at the different scattering angles for gas phase, and they found some changes. So here is this dipole forbidden thing that you saw before, and you see in the black that's a perpendicular, so you don't see much. But if you start looking out of the perpendicular, you start enhancing this, so it gets more and more visible. This is just free O2. And we have some very nice theory going on. I won't go into it, but if you want, the link is there to a paper to understand what is going on. And of course, since this was published, people thought, okay, this is another way to discern free oxygen molecules from bound ones, right? Because this is free, and this is something that you would see, this effect you would only see in this way in a free oxygen molecule. And one of the current ideas is that the one way to charge and discharge a battery, lithium-ion battery, is that you produce free oxygen in pores inside your battery material, and then as you charge it, and then as you discharge it, this is then bound back into the material. So this is one thing that a group from Oxford, together with a group from Såthe, have been doing experiments at Veritas to look at how can we use this effect and see it. First initial experiments, and then they tried to create an inoperando setup where they put anode materials on a window, and then you fill it with oxygen, and then you look at the effects of this. This is ongoing, and there's quite some discussion. There's a disagreement, let's say, that this effect is real or not, or is it something that's purely produced by the X-rays themselves. So this is ongoing, but it's worth noting, and it's something we can contribute to. So it's a nice effect. So that's another use of the O2 molecule, just basic molecular physics, to understand what's going on, and then try to use it as a tool. So main message for me is high resolution RIXS requires high brilliance, large instruments. It's one we have. You can determine local potential surfaces, of course, in chemistry, so that makes it useful. And then, of course, you have the correlated systems, which we'll hear more about tomorrow. And this is really the scope for the Veritas. I have to see how am I on time. Oh, I have plenty of time. So the scope for Veritas is to offer high energy resolution, good flux. We want to have a broad range of uses. That's why we designed the experimental chamber in this weird way that we have, and invented this novel experimental chamber that is small, so we can still develop other sample environments. And examples of where we need this is momentum transfer. We place a goniometer setup in UHV. But of course, we also want to do chemistry and energy materials. We have a liquid jet in operations, so people can come and measure solvents in liquids. We have flow cells where you can flow both liquids and gases. We have started working on inoperando battery cells, looking at charging, discharging, and changes in the electronics structure. We want to go into corrosion cells to find a partner for doing that. That's surface science. It's a tough sell for RIXS, but we hope. So that's it. I'll show you some more. This is just the same I had before. I'll just go into this end station overview, exactly what we did and how the philosophy and why it looks like it does. So we have the important part for the experiment, for the performance, is really the focusing mirror that produces this 1 micron spot. You want that to be stable and still. You have the spectrometer optics, you have the collection mirror, and you have the gratings. They can't move, because if they move, then your spectrum start moving. And then, of course, you want your sample to stay in the same place, so you're always shooting at the same position. So all these strings are mounted independently onto this granite slab that you see on the bottom. This is the basic philosophy of it. And that's why all the mechanics look like they do. So I'll be happy to show you the details when you have the practical. We can have a look at these things, exactly how it's done. But that's why you have this mess of engineering everywhere. But it all feeds into this idea to have this compact. And then, of course, we want a replaceable vacuum chamber, because we want to do UHV. We want to be able to look at the momentum transfer. So we need this UHV with the possibility of tuning the Q. Then we also want to be able to replace this. Oh, that's with something else. I'll show you that later. So we did some tests. This is while changing the angle of the spectrometer and continuously recording then the elastic peak, which is the same incoming and outgoing. And as you see, it is very stable. You need to retune it a little bit, but it's not like we lose the beam when we start doing this motion. So clearly it has been quite successful. We also have the manipulator is quite successful in looking at samples and imaging. So we had a user group who looked at ice, freezing ice, and they also wanted to freeze it at different temperatures for different configurations of the ice. And they had this honeycombed version. And again, it's important for us to know where we are of the sample. So this is then the image. So basically we have the X-rays, and then you scan the sample and you create this image, and you can clearly see where you have your sample and where you are on the honeycomb sample. And this is what I mean. It's very important to have this in combination. And then, of course, we have a dirty chamber for liquid jets. So this replaces then this Q chamber that we have. So we can just lift off the manipulator. We lift out the Q chamber and put it back. It takes about 1 week, but again, it's fairly complicated mechanics. But we can plan this, so we can plan a period of dirty experiments with liquid jets and gas phase and all of these things, and then we can just make this change. And this has been even further refined by our beamline scientists. So now I think we can run the inner atmosphere. We added some differential pumping stage on this, and added further differential pumping on the sides, more liquid nitrogen traps to collect all the vapor and everything. So I think now we can measure something like 10⁻² atmosphere in the innermost chamber, and still have good enough vacuum to be able to open and let the beam in. With filters, but still, this means that we can do a lot of things. And this is definitely one of the unique things with Veritas that you will not find anywhere else in the world. This combination of high resolution and this really ambient pressure-like conditions. Samples, as I said, we have this simple RIXS or simple manipulator setup. So this means that we have a form factor of our sample environment. It should look like this with all the measurements that we have. And then you get access to all the stability that we have. This means that we can tailor things with our users. If they come with an idea for a setup that they want to do, we can then collaborate and build a setup for you or with you. Typically, we need some money from you if you want to do that. But we do have a series of things that we also offer as standard, like a flow cell, which is in the middle, and the liquid jet on the right-hand side. And we have also liquid jets, both round jets and flat jets, if you want to look at that. We even have users come in with crossed two different liquids and look at the liquid-liquid interface between two different liquids. So we can do all those things. And yes, it is pink. That's I have a few more things. No, that was it. So I'm short. What questions?